Today we would like to introduce our recent research work, which has been accepted by IEEE Transactions on Automation Science and Engineering. This paper focuses on the motion planning problem of the aerial pick-and-place task. We propose a novel partially decoupled motion planning method for the aerial pick-and-place task. Compared to the state-of-the-art approaches, the proposed one has two novel features. First, it does not suffer from increased computation in high-dimensional configuration spaces. Second, collision avoidance for the delta arm is achieved through an iterative approach based on a pinhole mapping method. The geometric feasibility constraints are proposed to ensure the trajectories of the quadcopter base and the end-effector satisfy the geometry of the aerial manipulator. By using these constraints, we can plan the trajectories of the quadcopter and the end-effector, respectively. The overall system of the aerial manipulator is decomposed into three components. The first component is the motion planning of the quadcopter base. Compared to the existing methods for standard quadcopters, the proposed method has two novelties. First, the feasible grasping position is calculated for manipulating the object. Second, the flight corridor is divided into two stages, moving and manipulation stages. The second component is the motion planning of the delta arm. It is solved by an iterative approach based on a proposed pinhole mapping method. At each iteration, a quadratic programming problem is solved to determine the collision-free trajectory for the end-effector. A collision avoidance term, designed based on the pinhole mapping method and the GJK-based collision check results, is formulated into the QP problem, so that the aerial manipulator is driven away from the obstacles in the local environment. The third component is the controller of the aerial manipulator. The details can be found in our previous work. In the collision avoidance task, the effectiveness of the proposed method is validated. Without the proposed collision avoidance method, the length of the collision area is 0.026 meters. With the proposed collision avoidance method, the resulting trajectory is collision-free. The goal of the aerial retrieval experiment is to retrieve an object by the aerial manipulator. The span time of the experiment is 58 seconds. The computational time for calculating trajectory of the quadcopter is 43.9 milliseconds, while the computational time for calculating the trajectory of the end-effector is 25.7 milliseconds. To demonstrate the performance of our proposed method, we conducted simulations in Gazebo and compared its results with those of two baseline methods. Compared to the sampling-based method, our proposed method can reduce the computational time by 99.7%. Compared with the naive method, the proposed method performs better in terms of task duration. The proposed method can reduce the duration of the manipulation stage by 68.0%. The goal of the aerial transport experiment is to grasp an object and put it on the target location. The computational time for calculating the trajectory of the quadcopter is 45.6 milliseconds, while the computational time for calculating the trajectory of the end-effector is 32.8 milliseconds. Since the proposed method is computationally efficient, it inherently enables the capability for replanning. The goal of this experiment is to demonstrate the proposed method's capability to replan trajectories in response to changes in the object's position. The computational time for the original planning is 82.3 milliseconds, whereas the replanning process takes 36.2 milliseconds. This experiment demonstrates that the proposed method is capable of replanning. Thank you for your interest in our research work.